Welcome back to Inorganic Tutors Institute. In today's lecture, we are basically going to tackle 4 exams challenge problems under introductory analysis, right? Exams challenge problems under introductory analysis, right? So the first problem is, we want to prove that the limit of this function is equal to 1, right? As s approaches 2, right? So let's go through the process systematically so that we get to our destination, right? So step one, we want to prove that the limit as s approaches 2 of a function is equal to 1, right? Now, this will happen if we are able to define the epsilon delta well, right? So let epsilon greater than 0 be given, right? So we assume that epsilon greater than 0 has been given, right? Now, we must find delta, right? That is also greater than 0. So we must find delta that is also greater than 0, such that whenever we have 0 that is in between absolute value of x minus 2 and delta, right? So this absolute value of x minus 2 is between 0 and delta. Then it follows that the absolute value of the function minus the limit must be less than epsilon, right? So this is the definition for epsilon delta. Now, once you have been able to define this, the rest is algebraic manipulations, right? So first, that will be step 2. Step 2, we substitute the function into the expression, right? So we have absolute value of the function, which is this, x squared plus x squared minus 4x plus 5 minus the limit. The limit is here, 1, right? And this must be less than epsilon, right? So let's consider this. Simplify. When we are done, we add this to it, right? So let's simplify the expression. Right? So absolute value of x squared minus 4x plus 5 minus 1. When you simplify this, we are going to have absolute value of x squared minus 4x plus 5 minus 1, right? And this is equal to absolute value of x squared minus 4x plus 4, right? So this is what we have now, right? Now, this expression here can be factorized, right? So we have absolute value of x squared minus 4x plus 4. This is the same as absolute value of x minus 2 all squared, right? When you factorize this, this is what we're going to have, right? This basically means that repeated root, x minus 2 times 2. So it's just like s minus 2, x minus 2. So this is basically the same as this, right? So that is the expression we have there. Now, this expression that we have to understand that the absolute value of a square or absolute value of squares are non-negative, right? Absolute value of squares are non-negative. So we have to put that statement down, right? Now, since the absolute value of squares, right? The absolute value of squares are non-negative, right? They are non-negative. Any absolute value of a square is non-negative, right? So that is this expression, absolute value of x minus 2 r squared, right? So this expression is non-negative, right? So step 3. So this is basically step 2, right? So step 3. Let's try to relate this expression to the epsilon. Remember, we had less than epsilon here, and because we are trying to simplify the left-hand side, we ignore the epsilon. So let's relate that to epsilon. So we have absolute value of x minus 2 all squared to be less than epsilon. Right. So at this point, this is what we have, right? This is what we have. So this, we need to simplify it, right? And basically, this has to satisfy, or this will be satisfied if the absolute value of x minus 2 is less than square root of what? X, square root of epsilon, right? This will only satisfy if the absolute value of x minus 2 is less than square root of what? Epsilon, right? So this condition right here will only satisfy if the absolute value of x minus 2 is less than square root of epsilon. Right. So this is the condition, right? This is the condition. Now, let's choose a value for delta, right? Let's choose a value for delta. You know, delta will be epsilon, square root of epsilon. You know why? We stated in here that delta must be positive, right? And delta should lie, absolute value of x minus 2 should lie between 0 and what? Delta, right? So we choose delta to be what? Square root of epsilon, right? So we choose delta to be equal to square root of epsilon, right? For we choose delta to be square root of epsilon, this definition will hold, right? This definition will hold. So basically, we can say that if this is equal to, delta is equal to square root of epsilon, then whenever we do this, right? Whenever we do this, then we will have the absolute value of the function minus the limit to be equal to absolute value squared to be less than what? Epsilon, right? So let's write that in English here. So if delta is equal to square root of epsilon, then whenever whenever 0 is less than absolute value of x minus 2 less than delta, we can have the absolute value of the function minus the limit, which is 1, right? Minus the limit to be less than epsilon, right? And we know that this is equal to absolute value of x minus 2 all squared, and this is what? Less than epsilon, right? So conclusively, we can say that since for every epsilon greater than 0, there exists delta that is equal to square root of epsilon, such that 0 is less than absolute value of x minus 2, less than delta. This implies that the function, absolute value of the function minus the limit, right? Absolute value of the function minus the limit is less than epsilon. Hence, by the definition of epsilon delta, or by the definition of limits, we can say that the limits as s approaches 2 of x squared minus 4x plus 5 is equal to 1, right? So this is the conclusion. Okay, so this is problem number 2, right? If f of x is equal to this piecewise function, square root of x minus 4 if s is greater than 4, and 8 minus 2x if x is less than 4. Now, we want to determine whether the limit of this function exists as s approaches 4. Whether the limit of this function exists as s approaches 4. So first of all, we have to consider the right-hand side limit first. Then we check for the left-hand side limit. If both are the same, then we can say that the limit exists. Right. So we're going to start. Remember, this is introductory analysis. So each and every step is really, really needed, right? So we have f of x is equal to the piecewise function, which is square root of x minus 4 if x is greater than 4. And then we have 8 minus 2x if x is less than 4. Right? So first of all, consider the right-hand limit. Consider the right-hand limit, right? So we are going to consider the right-hand limit. If we do and simplify and we realize that the result we have is the same as when we do for the left-hand limit, then we can conclude, right? So we are going to deal with the right-hand side first. So limit as s approaches 4 from the right-hand side. So it means that 4 positive, right? So 4 positive of the function, right? 4 positive of the function. So this is equal to limit as s approaches 4 from the right-hand side of this, right? We are considering the positive one, right? We are considering from the right-hand side. So from the right-hand side, it must be greater than 0, right? It must be positive, right? Strictly positive. So you see, we have x greater than 4, right? And we have x less than 4. So if you are considering the right-hand side, then it must take the greater than sign, right? So we have square root of x minus 4, right? So that is the right-hand side, right? It must be greater than the value, right? So we are going to have limits as s approaches 4 from the right-hand side of x squared square root of x minus 4. Now, we're just going to substitute the value of 4 in place of x. So we have limit as s approaches 4 from the right-hand side of 4 minus 4, right? So we have square root of 4 minus 4, and that is going to give us limit as s approaches 4 from the right-hand side of square root of 0, because 4 minus 4 is 0, right? So we have limits as s approaches 4 from the right-hand side of 0. And we are very much aware that limit of a constant is the same constant, right? So we have 0, right? So from the right-hand side, the result is 0. Now, let's consider the left-hand side, right? So similarly, we are considering the left-hand side, right? So the left-hand side limit, right? So we are going to say that limit as s approaches 4 from the left-hand side. So that is going to be negative, right, of the function, right? And this is equal to limit as s approaches 4 from the left-hand side. Now, the left-hand side is 8 minus 2x, right? So we have 8 minus 2x, right? So this is equal to, when you substitute the limit, right, we are going to have 8 minus 2 into 2, right? So we have limit as s approaches 4 from the left-hand side of 8 minus 2 times 4 is 8, right? So we have this is equal to limit as s approaches 4 from the left-hand side of this will give us 0, right? And you know that from limit rules or limit theory, you know that the limit of a constant is the same constant. So we have 0. Right. So that is the result for checking for the left-hand side as well. So we realize that the result we obtain for the left-hand side is the same as the right-hand side. So conclusively, we can say that since both sided limits are the same, we can say that the limit exists, right? Since both limits are equal, since both limits are equal, we can conclude that the limits of the function exists. The limit of the function exists, right? The limit of the function exists. Hence proven. So that is all about limits, whether the limit exists or not. This is the process you go through to check, right? So if you have the function or if you have the piecewise function and you have to determine whether the limit exists or not, you have to check for the right-hand sided limit. You have to check for the left-hand sided limit as well. If the right-hand sided limit is equal to the left-hand sided limit, then we can conclude that the limit exists. All right. So to this particular problem, the limit exists. The limit exists. The limit exists. The limit of the function exists. Great. So this is question number 2. Let's move on to question number 3. Okay. So with question number 3, we want to prove that the limit of this function is equal to 4 as s approaches 2. So this problem is just like question number 1, right? So we are going to go through the same process, right? But in this case, we have to bound we'll get to a position where we have to bound the expression, right? So let's start with the whole process. But remember the definition of epsilon delta, right? We are going to go through the same process as we did in question number 1. So in here, we want to prove that limit of a function as s approaches 2 is equal to 4. Remember, this is introductory analysis, so each and every step is needed, right? So the limit of a function as s approaches 2 is equal to 4. That is the first step. Second step, we have to define the epsilon delta, right? So epsilon delta definition. So for every epsilon greater than 0, right? For every epsilon greater than 0, there exists delta that is also greater than 0, right? Such that whenever 0 is in between 0, x minus 2 is in between this two data, right? 0 and delta, right? Then it follows that absolute value of the function minus the limit must be less than epsilon. This definition is required everywhere. So this is what we have. We have been able to define, right? So the next step is to substitute the function inside what we have defined, right? So step 2, right? So we're going to substitute the function. So we have x squared plus 2x plus 1 minus 4, right? And that must be less than epsilon, right? So we have absolute of x squared plus 2x plus 1 minus 4 less than epsilon, right? So we have absolute value of x squared plus 2x minus 3x minus 3 is what? Less than epsilon. So this is what we have, right? So let's consider the left-hand side and deal with it. When we are done, then we relate it to the epsilon, right? So considering the left-hand side, x squared plus 2x minus 3, we have to handle this part very well, right? So what we have to do in here is to factorize the inner expression. And you know that this quadratic expression that we have here, we can factorize it to have x minus 1 and x plus 3, right? So the absolute value of x minus 1 and x plus 3, right? So if you factorize this is what you are going to have, right? Now, we have to make sure that we control the expression. So this expression, you realize that we don't have s minus 2 in it, right? We don't have s minus 2 in it because we have to get s minus 2 to be able to substitute delta, right? So we have to control this expression so that we can, depend on the x minus 2. We can depend on s minus 2, right? So we need to bound this. And how do we bound this? We have to make sure that we find a term that is near x equals 2, right? So we have to find a term that is near x equals 2, right? So we assume that absolute value of x minus 2 is less than 1, right? We are finding a term that is near x equals 2, right? So we assume that absolute value of x minus 2 is less than what? 1. So if that is the case, we know that this absolute value of x minus 2 contains both positive and negative. So this is, if you remove the absolute value, you're going to have a plus or minus s minus 2, right? So you do that and you're going to have 1 less than x less than 3, right? Because if you send this here, you're going to have plus 2, which is going to be 3. If you bring this here, you're going to have positive 1, right? So that is how it's going to be. Okay, so this is the result. All right. So we are going to use this expression to bound this. Right, so first of all, we assume that absolute value of x minus 2 is less than 1, this absolute value. So now you add 3 to both sides, right? So you add 3 to both sides and you're going to have 4 less than x less than 6, right? So this is what you are going to have, right? You add 3 to both sides. Okay, remember there is s plus 3 here, so you're going to have 4 less than x plus 3 less than 6 and less than 0 less than x minus 1 less than 2, right? So this is what we have, right? This is what we have. Now since you have been able to bound the expression, we have absolute value of x plus 3, x minus 1 to be less than or equal to 6, right? 6 times absolute value of what? X minus 1, right? And also we have x minus 1, absolute value of x minus 1 to be equal to x minus 2 plus 1 less than or equal to absolute value of x minus 2, right? Plus 1, okay? Plus 1. So we have plus 1 here, okay? So this is basically equal to absolute value of x minus 2 plus 1 less than or equal to absolute value of x minus 2 plus 1. Okay, so now we can say that hence absolute value of x squared plus 2x plus 1 minus the limit is less than or equal to 6 times, right? 6 times big bracket absolute value of x minus 2 plus 1, right? Right, so this is what we have. Now we have to choose a very small bound, right, to be able to simplify this, right? So we choose delta to be equal to a minimum of 1, and epsilon on 12, right? So this is what we do. We choose delta to be equal to a minimum of 1 and epsilon on 12. So this is going to be the value for delta, right? To be able to bound this, we have to choose a very small value for delta so that we can bound this expression, right? So this is what we have. So then whenever 0 is less than absolute value of x minus 2 less than delta, we can have absolute value of x squared plus 2x plus 1 minus 4 to be less than epsilon. Therefore, by the definition by the definition of limits, or by the definition of epsilon delta, we say that limit as s approaches 2 of x squared plus 2x plus 1 is equal to 4. Right? So this should be your conclusion. So this is the end of the problem. This is the end of the problem. Okay, so with question number 4, we want to prove that the function f of x is equal to 1 minus square root of 1 minus x squared is continuous on the interval, on this closed interval, right? Negative 1 and 1, right? The intervals are closed, negative 1 and 1, right? So first of all, this is continuity, right? A problem of continuity, right? So we have to go by that, right? So first, state the problem. F of x is equal to 1 minus square root of 1 minus s squared, right? On this interval. Okay, so we just want to prove that this particular function, right, is continuous on this particular interval, right? We want to prove that this function is continuous on this interval. All right. So first of all, we have to write the definition of continuity, right? So step 1, definition of continuity, right? So this is the first thing we have to do, right? So a function is continuous. A function is continuous at a point. Let's say A, right? At a point, let's say A. If the limit as s approaches A of the function A is equal to the function A, right? If the limit of a function A is equal to the function A as as s approaches A, right? So this is the definition of continuity. You have to write this. You have to write this. A function is continuous at a point A if the limit of the function A is equal to the function of A as s approaches A, right? So from there, then you come and state the epsilon delta definition. So for every epsilon greater than 0, there exists, right? I'm using the symbol or the notation for there exists. So, right, there exists delta that is also greater than 0, such that whenever absolute value of x minus a is less than delta, right? It's less than delta. So in here, absolute value of a, which is the value or the points, right? The point x minus the points is less than what? Delta. Right. So this is what you need to begin the process. You have to state this definition to begin the process. Right. So, if you state this, then it means that we can say that if the absolute value of the function minus the function of the points, right? The function of the points is less than epsilon. It's less than epsilon. So whenever x minus a is less than delta, then we can say that the absolute value of the function minus the function of the point is less than epsilon, right? So this definition is very, very important. This definition is very, very important. So if this definition holds for every point A in an interval, right? The interval is a closed interval of which is -1 and 1, right? Then the function will be continuous on this interval. If this holds, then if this holds on the point A, then the function will be continuous on this interval. But if it fails, then it will not be continuous on this interval. I take it again. If this condition holds, then, right, let me take it this way. If this condition holds for every point, that is the A, then the function will be continuous. This function will be continuous on this interval, this closed interval, -1 and +1. So step 2, we can use the domain, right? We can use the domain of the function to determine whether this point or this interval is closed, is continuous on this function, right? So step 2, domain of the function. Domain of the function. So if we are to use the domain of the function, then what we have to do in here, remember, if you want to find the domain of a function and the function is under the set function, then you have to make sure that any expression under the set must be greater than or equal to 0, right? So that is the statement. The expression or the argument under the square root sign must be greater than or equal to 0. So you have f of x is equal to 1 minus square root of 1 minus x squared, right? This expression or argument under the square root sign must be greater than or equal to 0. So we have x or 1 minus x squared to be greater than or equal to 0, right? So we say that 1 negative x squared greater than or equal to -1, right? So we have x squared to be less than or equal to +1, right? So this means that x lies between -1 and +1, because if you take the square root on both sides, you're going to have plus or minus 1, right? So we have x is less than or equal to plus or minus 1. So this means that the interval, this function here, is continuous on this interval, right? So we say that this function is continuous on this interval, less than or equal to 1, right? So this is the interval. You see, if you use the domain, it works perfectly, right? So hence the function is defined on this interval. So this is one step. Hence, the function is defined on the interval -1 and 1 closed, right? So this is the first part of the definition. Now we have to go to the epsilon delta definition as well. So remember to do that. This is first step. The second step, we are going to use the epsilon delta, right? So let's go that way. Let's go that way. So this step is where we use the epsilon delta definition. So we let A be an arbitrary point. A be an arbitrary point in the interval. So you let A be a member of the interval -1 and +1, right? A be a member of the interval -1 and +1, right? So if A is the member of the interval -1 and +1, then then we can say that the function of the point A is equal to 1 minus square root of 1 minus what? A squared. Because we are saying that A should be the point, an arbitrary point in the interval. So we are going to use A to represent the X, right? So this can clearly tell us that this point is an arbitrary point in the interval of -1 and +1, right? The next step is we have to form the expression, right? So forming the expression of which we have into brackets 1 minus square root of 1 minus x squared minus 1 minus square root of 1 minus a squared, right? This is the function that we formed. So remember, we defined A to be an arbitrary point in the interval. So the point is what we use as the limit, right? So we are using this point as the limit. Remember, if we are defining the epsilon delta, if we have the limit on the right hand side, we use the limit over here. But in here, we don't have the limit. So we have to define an arbitrary point on the interval. And that is what is happening here. So we move up here. Then we're going to have absolute value of 1 minus square root of 1 minus s squared minus 1 minus square root of 1 minus a squared, right? Absolute value. Now, you could see clearly that this will take off this, so we have absolute value of negative square root of 1 minus s squared. Then this becomes positive, right? So we have plus square root of 1 minus a squared. Absolute value. So clearly we can see that we can position this first and position this second because this is positive and this is negative. So we have absolute value of square root of 1 minus a squared minus square root of 1 minus x squared. Right. So this is what we have. Now, at this point, we have to rationalize it. How do we rationalize? We have to multiply by the conjugate, right? So this is going to be absolute value of square root of 1 minus a squared minus square root of 1 minus what? A squared, right? So this one times the conjugate, right? So the conjugate here is going to be square root of 1 minus a squared plus square root of 1 minus x squared divided by square root of 1 minus a squared plus square root of 1 minus s squared. Right, so we multiply by the conjugate, right? We multiply by the conjugate, right? So this is what we have. So we have to simplify this, right? So let's put this in a bracket so that we can see that we are multiplying that step. Right. So if we do that clearly, we are going to have this will be equal to this expands this expands, this expands this expands that. So you realize that you'll be having difference of two squares. Right. So this will give us absolute value of 1 minus a squared, absolute value of 1 minus a squared minus 1 minus x squared. Right. Absolute divided by square root of 1 minus a squared plus square root of 1 minus s squared. Right, so this is what we have. Now, this term that we have, we can see clearly that we can expand the top and clear off some terms, right? So we have absolute value of 1 minus a squared minus 1 plus x squared divided by square root of 1 minus a squared plus square root of 1 minus s squared. So this takes off this, and then we have absolute value of x squared minus a squared divided by square root of 1 minus a squared plus square root of 1 minus s squared. Right, so you can see clearly here that this is difference of two squares. Right, so let's come up here. Right, so we simplify this. Since this is difference of two squares, we are going to have absolute value of x minus a times x plus a, right? Times x plus a absolute divided by the square root of 1 minus a squared plus square root of 1 minus x squared, right? Now, we have to bound this expression, right? How do we bound this expression? We have to make sure that absolute value of x lies between positive 1, and then absolute value of a also lies between positive 1. So we have to bound this expression. We have to bound the expression, and so we make sure that the absolute value of x lies between positive 1, and also absolute value of a lies between positive 1. Right? So this is going to give us this, this is very clear. Everything is clearly explained. So from here, you can easily do it by yourself, right? So we can see if absolute value of x is less than or equal to 1, and absolute value of a is also less than or equal to 1. Remember, a was defined as an arbitrary point in the interval. Right, so if absolute value of x is less than or equal to absolute value of a, then we can say that, absolute value of x plus a should be less than or equal to absolute value of a plus absolute, or we can equally say that absolute value of x plus absolute value of a. If you are using the equality sign, inequality, right? So absolute value of x plus a should be less than or equal to absolute value of a plus absolute value of what? X, right? And this must be less than or equal to 2, because we said from here that absolute value of x should be less than or equal to 1, and absolute value of a should be less than or equal to 1. So this is 1, this is 1, so it makes what? 2. So it means that this term here results to less than or equal to 2. Therefore, we can say that less than or equal to 2, this term here is less than or equal to 2 times, this is what we bound, right? We bounded this. So it means that this term here is 2 times the remaining one, right? So we have less than or equal to 2 times the absolute value of x minus a divided by square root of 1 minus a squared plus square root of 1 minus s squared, right? So now we have to make sure that, or we can clearly observe that the absolute value of x plus a was here. And this is what we bounded. And we realized that if we use the inequality, we can have this. And this is what? Less than or equal to 2. So if this is less than or equal to 2, then we can substitute here to have what? 2 times the absolute value of what? X minus a divided by that. Now, we can observe that we can observe that the absolute value of square root of 1 minus, we can observe that the denominator, which is square root of 1 minus a squared plus square root of 1 minus s squared, is greater than or equal to square root of 1 minus a squared. Right? We clearly could see that if you sum these two, is greater than or equal to the absolute, the square root of what? 1 minus a squared. Right? So that's clearly from the function f of x minus the function of the point less than or equal to 2 times absolute value of x minus a divided by the square root of 1 minus a squared. Right? So this right here, right? This right here, we could clearly say that absolute square root of 1 minus a squared plus square root of 1 minus s squared, if you sum these two, it should be greater than or equal to this term. Right? The summation of these two should be greater than or equal to this term. So choosing delta, we have to let epsilon multiply this expression, right? So this is the expression that we are choosing, right? So we have to let epsilon multiply this expression. Then if the absolute value of x minus a is less than delta, we have the absolute value of f of x minus the function of the points should be less than the 2 times of this divided by that, right? And so we see that this will be less than the expression here. This will be less than the expression here, 2 over the square root of 1 minus a squared times the absolute, the epsilon times what? Square root of 1 minus s a squared divided by 2. And this, we can clearly see that this cancels this and this also cancels this. So we see that epsilon remains. So we come here. We say that thus for every epsilon greater than 0, there exists delta that is also equal to epsilon times square root of 1 minus a squared divided by 2, right? Such that absolute value of x minus a less than delta implies that absolute value of f of x minus the function of the points is less than epsilon, right? So this is how we conclude. So we can basically say that, therefore, by the definition of the limits, the continuity limit, we say that, therefore, limits as s approaches a of the function equals the function of the points for every point that we pick in the interval of -1 and +1 of -1 and +1. Hence f of x is equal to 1 minus square root of 1 minus a squared is continuous. Is continuous on the interval -1 and +1. Right. So this should be your end point. That is for every epsilon greater than 0, there exists delta. That is when you take epsilon, multiply epsilon by square root of 1 minus a squared, divided by 2 such that the absolute value of x minus a less than delta. This implies that the definition we had earlier from the beginning will be less than epsilon. Therefore, the limit of the function x as s approaches a is equal to the function of the points for every point that is in the interval. Hence, we can say that the function of the function f of x is equal to 1 minus what? Square root of 1 minus a squared is continuous on the interval 1 minus 1. Closed. Great. So this is the end of the exams challenge for 4 problems on introductory analysis. Thank you very much for watching. I really appreciate your time. Don't forget to subscribe, share with your mates, and I'm going to give you more updates. Bye-bye.